Thank you, Cloud Person. All right, why don't we get started? Good afternoon. Welcome back from, I guess, the weekend since I last saw you all. Today is purposed with talking over a whirlwind tour, as it were, of various topics and concepts that one would do in a standard electrical engineering curriculum. And by the end of today, I hope to give you sufficient enough background for our purposes, because part of what we'll do during this semester is build some circuits, okay? All right, but before we begin, some administrative bits. Project one, as you all know, is due this evening. Please make sure you do not wait until the last minute. Of course, it is a group exercise. It would be helpful if everyone in the group submits their own submission, because you'll also, among your materials, be submitting your MBTI, Myers-Briggs type from your test, as well as your reflection about the group dynamic. So please make sure each group member, I should say, is handing in separately. The reading has changed, and what I like to do is keep a running list of all the reading assignments, and it's up on the Moodle site. Please make sure you're checking the Moodle site. I've curated a lot of information there for your benefit. The reading has changed. It's up there. From digital outputs to pulse width modulation, or PWM, pages 23 through 31 in the Arduino book. Make sure you're watching the videos that I've curated, in specifically watching the undergrad examples of the 4 points. That'll be important for Friday, as well as the videos for the 4 LED bounce chaser, as I'm calling it. Project number 2 will be out after finish writing it up, out on the Moodle site. It will be due a week from today at the usual 11:59 and 59 seconds. And this should be a fun one to get you doing something that works as soon as possible. And this will give you some experience with the digital I/O pins, and you'll use that to drive some LEDs, and we'll talk about LEDs today, among other things, in an interesting application. But the goal is to have you implement it as a finite state machine. And on Friday morning session, I'll go over a recipe for implementing a finite state machine. And we'll talk a little bit about why that particular construct is important. Okay, any questions about this, about what to do this evening? And some of you have already handed it in. Thank you for that. For those of you who haven't handed it in, please do not wait until the last minute. For those of you who had me last semester, I'm up late a lot on Slack. If you have any questions, please pose them to Slack. And I recommend, if the question is not of a personal nature, please post it on the class Slack channel so that others can benefit from that question and answer interaction. Because I promise you, if you have a question, probably a third to a half of all of your colleagues also have the same question. Okay? All right, and this semester, that's the goal, cross my fingers, cross my toes, to try to go to bed earlier. So by 10 p.m., that's my cutoff to answer questions, even though it's due a second before midnight. But any questions? No questions? No? Everyone having a good first week? Yeah? All right. Anyone want to stretch and kind of get the blood flowing in this cold room? No? Okay. All right. So why don't we continue? So students ask me all sorts of things, and one curiosity I got is someone said, Holness, you wear the same thing every day. Well, I don't wear the same exact thing every day. Ever since high school, I've been this way since high school. I've borrowed what Steve Jobs, co-founder of Apple, has done, and he considers it a uniform to have a black mock turtleneck, which I followed, but I don't like the blue jeans so much. I have khakis. And if you look in my closet, I have 8 to 10 black mock turtlenecks, different weights, and khakis of various brands and styles, right? So I don't wear the same thing. Just let's get that out of our minds. I just like my uniform because it suits me well, and I've been that way for a long time, and I'm never going to change. Okay, and I don't advocate you do it or not do it either, right? So don't show up and that freaked me out if everyone showed up in black mock turtleneck. But anyways, I digress. So why don't we get started? So where we last left off, we talked about the Arduino board, and we talked about different form factors. And the reason for that is that when you're doing any kind of hardware design, system design, you want to choose the right platform for your application. And so some applications warrant a lot of I/O, like we saw with the Arduino Mega. Some warrant a very small size, physical, so you might want the Nano. But nonetheless, when you have an application, unlike software, well, maybe it's a little bit like software, but even more so for hardware, you're really constrained on cost, but also this form factor. And that form factor impacts two things, both the amount of memory that you have available, as well as the computation. And let's throw in this third one, the so-called power budget, because that's going to impact what you're able to do. Okay. We also talked about this idea of these daughter boards, so-called shields, that you can plug in to the base Arduino, the credit card sized Arduino, like the Uno 3 and variants like the Wi-Fi revision 2. And you can use these shields to extend its capabilities. Things like the GSM shield are immensely useful because it allows you to engage in telemetry using the wide area over the cell phone access network. And that's particularly important for applications where you're doing monitoring over a large area where you might not have Wi-Fi reach. We also have shields that implement things that you could do in software on the Arduino board. And the reason for that is because when you implement something in silicon, in hardware, you can make it run very, very fast through a simple API call. And we gave some examples of that. Then we also looked at the Arduino IDE, which is for free from arduino.cc. And I'm pretty sure someone will gladly charge you for all sorts of variants of the things you can get for free. But when you bring up the Arduino IDE, you have two entry points. And I forgot about this room and the flashing of that screen, something kind of wonky about this connector. When you bring up the IDE and you start a base program, there are two entry points for any Arduino sketch, as it's called, a subset of C++. And the sketch has a setup routine and it has a loop routine. The setup routine, we said, is called when you power on or reset the power for your board. It's called one shot. So if you reset it again, it'll call that setup each time, just once. And that setup routine is purposed with putting your code that establishes settings. One of the settings that we'll see on Friday is whether your digital I/O pin is going to be for outputting plus 5 volts, 0 volts, or for reading or inputting plus 5 volts and 0 volts. And so this loop routine, after the setup is called, this loop routine is called periodically. Well, it's called again and again and again. Once this loop block, that routine enters, it executes, it exits, and then it's called again. And it's called again. And this loop routine is where you put your program code. And on Friday, where you'll be putting your implementation of a finite state machine. Okay, any questions about this stuff? No questions? No? All right. So lastly, we talked about the compiled sketch language. And this is different from something like Java or Python. Java is compiled, kind of, it's quotation marks, but it's compiled for a virtual machine. Now, certainly you can cast this virtual machine for Java in silicon, absolutely, right? Java chips are very commonplace. Or you can have this virtual machine implemented, embedded within an operating system, which is typically the case. With Python, of course, you have your Python code. Each line of the Python code is read by the Python interpreter, and it's this runtime for Python that implements the semantics or the behaviors associated with each of those parsed commands. But in the compiled language, it's a little bit different. Your compiler, as we said, is translating from the language, which is nothing more than a set of commands in text, to the bytecode, which are the ones and zeros, the byte sequence that's understood by the native processor. And so in this compilation, it proceeds in two phases. This, number sign include says, let me take the name of the file identified in the angle brackets, in this case, spi.h, read it off the file system, and paste it in place of where that number sign include directive is. And that's typically used to bring in definitions for library functions. When you're in Java, when you say import statement, you're bringing in libraries. In similar fashion, in C++, you're bringing in the definition of other functions identified in this spi.h file in this example. But for C, that bringing in of libraries is a little bit different. You bring in the definitions in the source code, but you also need to glue together the bytecode for those libraries on the tail end, and we'll talk about that in a few seconds. So once you do this translation, the other one is number sign define. A number sign define is nothing more than a replacement. Number sign define, the name you want to call it, in this case, num underscore iter, and a space, and then another string. It could be a number, it could be characters, it could be a name, what have you. And so the preprocessor does replacement based on those preprocessor commands you specify, and that gives you another modified version of your program, which is then pushed through the compiler, which translates it to the bytecode understood by the processor. But this bytecode or machine code is your machine code, is not the machine code for the libraries that you're using. Those are implementations, those are software. And so the other part, the linker, takes those libraries, it loads it into memory, and it glues together the library machine code with the machine code for your program, and that's what gets staged and loaded onto the processor. Okay, any questions about this? No? All right. And so this is engineering stuff. And one of the things you learn very quickly in any sort of engineering-based course is trial and error is a thing, right? So don't get discouraged when you try something, it fails, you try something, it fails, you try something, it fails. Try it again, you're just so sure you got it right based on the circuit diagram, and oops, you forgot your ground wire. And now all of a sudden it works. And you will dance for joy. And in honor of all of the scientists that make this possible, this is our official theme song for the course. It's just electricity. I come from a dancing culture, so there you go. That's not going to be on the final. So anyways, what is this thing we call electricity? People kind of use it every day. It's immensely useful. But what actually is it? Anyone kind of give consideration? What's electricity? Yes. The flow of electrons. Ah, I'm taking physics, right? Awesome, thank you. It's the flow of electrons. So this electricity is immensely useful, and it was one of the major breakthroughs in human society because you can heat with it, you can cook with it, you can see with it, you can travel with it, all sorts of stuff. And so in electrical engineering, you learn ultimately skills that'll help you design, develop, and manage the manufacture of electronics. But to do so, depending on what you're after, you have to understand some of the underlying physics. And depending on what you're doing, much of the underlying physics. And so in electrical engineering speak, you say you're a double E, right? And double E's, in the case of this class, we're going to be doing digital circuits. So you're going to have to learn a little bit about logic design, embedded systems. We're also going to be doing a little bit of analog circuits. So you're going to have to learn a little bit about power, voltage, current. But this is sort of a high-level description of various sub-areas in electrical engineering. And the takeaway here is that you're going to have to learn a little bit of the underlying physics, okay? All right, so we have to do this. So what exactly is electricity, okay? So someone said it's the flow of electrons. Absolutely. Now, everything, matter, is made up of atoms. And if you get an electron microscope and you zoom in, atoms are made up of two major components. We have the nucleus, and that nucleus is comprised of other things. Take a high energy physics course, but in this course, of something called neutrons, which have no charge, and subatomic particles called protons, which carry a positive charge. Now, around this nucleus, moving around in elliptical orbits, just like the planets orbiting the sun, are these negatively charged particles, are electrons. And so these electrons are spinning. Now, this spin, in terms of planetary motion, is because of gravitational attraction. Any two bodies that have mass are going to attract one another. But in this case, it's not Newtonian gravitational attraction, it's electrical attraction. It's a little bit different. But nonetheless, these electrons move in orbitals, and there are multiple orbitals around which these electrons orbit the nucleus. And in these orbits, they give them names. They're called valency levels or shells. You have an innermost shell, and you have some intermediate shells, and you have an outermost shell. Now, of course, the number of electrons, or rather each shell or valency or orbit, takes a maximum number of electrons that can orbit in that valency, as it's sometimes called. The innermost has 2 electrons occupying its slots or space orbiting. The next one has 8, etc. Now, each holds a certain number of electrons, but what makes a substance or matter different from another, like carbon versus hydrogen and so forth, is the arrangement of electrons in these valencies. Okay. And so these particles have an interesting property in that 2 particles that are opposite from one another in their charge, namely a positive and negative, are going to attract one another. They want to come close to each other when they're in close enough proximity. And 2 similarly charged subatomic particles are going to want to flee or repel one another. So there's an attractive force and there's a repulsive force. So this idea of these orbitals is not arbitrary, and regardless of the substance, that it is the case that the preference is to have all of these valencies completely occupied, all the slots full. And so any substance for which all of its valencies are completely filled, those are stable. Something that's not completely filled in its valencies is therefore unstable. Things like to be stable, right? And so an atom will do everything possible to try to fill all of the vacancies in its valences. That's what it wants to do because it wants to go to stability. Okay. Well, how does it do this? It does this by donating or accepting an electron from a nearby other atom. It also can do this by sharing an electron with another atom. Now, when you donate or accept an electron, that's called a chemical reaction. And that's exactly what chemical reactions are, swapping all around of all of these electrons between valencies. The sharing of electrons, well, both of those atoms, like 2 siblings, fighting over a toy, they're not going to let go. That's called a chemical bond. And so this bonding process is when 2 atoms share the same electron in order to go to stability, this filling of their valencies. Okay. Any questions about this? So why am I talking about electrons? Okay. Well, let's continue on with this idea about donating or sharing these electrons. Now, an electron that can be donated or accepted is a so-called free electron. And these free electrons typically exist at the outermost valencies. Why? Because when you fill the valencies, you fill from the closest orbital, making your way out to the larger orbitals. And so if you have vacancies, those vacancies in an orbital or valency is more likely to be at the extremes, the exteriors. And so we have this sharing, rather this donating and accepting of an electron. On the left, we have a free electron. It moves out of its valency off to some other atom. And here, the recipient of this free electron it takes it into its valency because it wants to go to stability, its chemical reaction, and it fills its valency with this free electron. Okay, and so there are some materials called conductors that make it really easy for these free electrons to move around. Now, I'm not a chemist. I hated chemistry. That's why I'm a computer scientist, electrical engineer, but they made us take chemistry. But this idea of free electrons has to do with how vacant your valency is on the outermost orbital. And so a conductor is a material, an atom, for which the flow, this donation or accepting of free electrons, is quite easy. The converse of that is something called an insulator. An insulator is one that makes it very difficult for these free electrons to be accepted or donated. Now, gold, most metals are great conductors, and gold is the best conductor out there, but there's a problem. It's very expensive. So because it's so expensive, you'll only see gold conductors where it matters. Sometimes in stereo equipment, you see gold-tipped jacks where you plug things in. In satellite electronics, they often use gold. Why? Because it's really expensive to go and retrieve it if you need to fix it. For bonding, as we saw, a silicon chip to the pad frame, they use gold because that connection really, really matters, and those chips are expensive. Any questions? It is, I'm glad you asked that, it's in between, and I have the next slide about that. And so insulators are things like plastics, wood, glass, and it's not to say you can't pass electricity through them. You just can't pass electricity or the flow of electrons through them very easily. Okay. And so there's something called a semiconductor. And a semiconductor, as the name implies, it's kind of a conductor and an insulator at the same time. It's in between. Now that means the semiconductor can vary or be made to vary how it passes, how it gives or it accepts these free electrons. Now, what happens with a semiconductor, it's made out of silicon, and the silicon is refined, and it's formed into what looks like deli logs. You know, when you go to the deli, you get like half a pound of turkey, but instead of using a slicer, they use a laser to cut these things into thin slices called wafers. And here, this is a silicon wafer, and this is that deli log, as I'm calling it casually. It's more formally called a silicon ingot, right? Like a gold ingot, but this one's round instead of rectangular. And so you take these wafers and you change their valencies through one of two major categories. One's called sputtering. So you introduce other chemicals or materials called impurities, and they're called impurities because they change the valency of the raw silicon. Now, the other one is called photolithography. And photolithography is almost like screen printing a t-shirt. You're taking a thin film of some material, almost like paint, and you're applying it in specific patterns to change the conductive properties of this silicon in various ways. Specifically, you're constructing transistors. Okay? All right, any questions about this? No questions? No? All right. And so one of the key pieces of terminology that you hear in circuits is something called ground. And ground refers to what's called the ground state. And the ground state is the lowest energy state of an atomic particle. Now, ground means that you have a net zero charge. What does that mean? It means the positive elements, the protons in the nucleus, have the same number as the negative elements orbiting in the valency levels, the electrons. So if you have equal numbers, positive, negative, the net sum is zero. And so when you have a ground state, that is the most stable state a particle can be at, because its net charge is zero, it's less likely to donate or accept any more electrons. Okay. Now, the other thing that's important about the ground state is when you reach this net zero charge associated with your subatomic particle, it's not going to give out any radiation. It's not going to send out electrical energy, and it's not going to send out magnetic energy. So it's very, very stable, right? Energy is not going to move. It's not going to change on its own. Okay, any questions? No? All right. And so how do you get more negative? Well, when an atom gains electrons, it gets more and more negative. Likewise, when you donate electrons, you get more and more positive. The protons don't change. Now, I'm not a nuclear physicist. You're going to have to ask them about nuclear reactions, right? But for our purposes, you can change your ground state by either accepting free electrons or donating free electrons. Okay. And so just like what happens in kinematics, the physics of mechanical energy, if you were to take a ball and you put it at the top of a hill, that ball wants to go to a stable configuration. It has stored energy, so-called potential energy. And if you were to release it, it converts that potential energy to kinetic energy, energy of motion, until it reaches the ground state, which is the lowest energy level that is available to it. And so when you have a large amount of energy accumulated, you can use that energy to do work. You have to release it through motion in order to get it to do work. Now, one of the things that you've probably experienced, particularly in the wintertime, because in the wintertime, the air is more dry, less humidity, and water is not a very good conductor. Now you're walking along the hallway, and when you're walking, your shoes are rubbing on the carpet. When you're rubbing on the carpet, you're adding energy and you're transferring electrons from the atoms in the carpet to the bottom of your shoe. As you keep trudging on the carpet, that energy accumulates more and more and more, and all this charge is all over your skin. Because remember, free electrons can travel. If you accumulate enough free electrons, it'll be on your skin, it'll be all over you as you walk. Now, you come in close contact to something that doesn't have as much energy, and those electrons say, ha, I have a way to get to this other place where there aren't as many electrons packed in, and it jumps, and you get static electricity, static discharge. Okay. And so the doorknob in this case, it could have a positive charge, it could have a negative charge, or it could have a net zero charge, but you have more charge accumulated on your body with no place to go. Once you get close enough, boom, there's your static discharge. The same thing happens with lightning, this flow of electrons. You have mechanical energy in the atmosphere. Hot air rises, cold air falls, so you get this churning in this vortex. The air molecules are rubbing up against one another and charge is accumulating. The charge accumulates so much, it has no place to go. And it says, down there, boom, you get lightning. Now, lightning might seem very frightening, but the safest place in a lightning storm is in a metal garbage can or in a metal car. And that's due to something called Faraday's principle. All of the flow of charge stays at the valency. It doesn't go inside the conductor. And if you're inside the shell of a metal car, lightning strikes, it'll be horrific. And I've been on the Delaware Memorial Bridge with lightning striking on both sides. Like, oh, God, please. But anyways, inside of a conductor, there is no charge, no electric field and no magnetic field. And that's because the electrons, free electrons, stay on the valencies, the outer shell. Okay? And so in similar fashion, we have this injected energy. This charge gets built up, these electrons accumulate, and they need some place to go. And they do that through motion. Okay, any questions about this? No? All right. And so charge is not created. I'll say it again. Charge is not created. It's merely transferred from one place to another. Moreover, energy is always conserved. And so when you say a hydroelectric plant or a solar farm is generating electricity, no, it's not. Hydroelectric plant is converting mechanical force into electrical energy, and the solar energy plant is converting photon energy into electrical energy. Okay? That's a really important concept that we'll need for later. And so what is this charge? This charge is the unit of measurement as a consequence of the existence of protons and electrons. Notationally, if you look through the EMAGs, electricity and magnetism text that I posted or PDF in the resources, they'll say charge using a symbol called Q, and that's a standard double E thing. And the unit of charge is called a coulomb. Coulomb is the last name of the scientist that did a lot of the pioneering work. You make a discovery in electrical engineering or an algorithm computer science, you can name it after you or name it whatever you want, right? But that being the case, a so-called elementary charge is this unit of charge associated with a single proton, which is positive, or a single electron, which is negative, noted positive E for the proton, negative E for the electron. And so if we look at the amount of charge for one electron, that's negative 1.6 times 10 to the minus 19 coulombs. That's a really small thing for one electron. But if we look at 1 coulomb worth of charge, that's quite a few electrons. That's 6.24 times 10 to the 18. That's a count electrons, okay? And so a coulomb is the unit that is used to measure the accumulated charge, because it's kind of hard to say, we have this many electrons, this is what we're going to do with it, right? You need some other units to make this all a little bit easier. Now, proton is the same, except the sign is positive. All right, any questions? No questions? No? All right. So one of the things people say is, I'm going to store charge in the form of a battery, right? And these are different batteries people have come to know. Now, in the center, I won't mention the brand name because they're not giving sponsorship. I'm capitalist. These are so-called nickel-cadmium batteries. And one of the ways you can, quote unquote, store charge is through a chemical reaction. Now, you notice you use these nickel-cadmium batteries, after a while, they stop working. They stop supplying charge. And that's because the chemical reaction, this exchange of electrons, it peters out, right? There's no more unreacted atoms left. The other type of batteries, this nickel metal hydride, rechargeable, lithium polymer, lipo, lead acid, typically when you describe a battery, you describe it based on the chemical substances that are in these batteries. Now, for the lead acid, the lipo, and the nickel metal hydride, those batteries also have a kind of chemical charge, but you start out by injecting charge into it. You apply electricity to them, and this electricity reorients the arrangement of the electrons, and you take off that energy you've injected, and now you can use it, and it gets spent. And then you apply electricity again to it to reorient those electrons again. Now, of course, this doesn't last forever, because after a time, the mechanism wears out, and even rechargeable batteries can be spent, okay? But any questions about this? No? All right. And so the idea then is you take these devices that can store charge, these batteries, or I say store charge, I'll just use that parlance. You put enough of them together, and you can do all sorts of fantastic things, like run a Tesla, right? I could have said Ford Fusion, but or name any other Volt, Chevy Volt, or what have you. But nonetheless, let's look at how you store this thing and this idea of charge in motion. Now, the movement of free electrons is called current. And as we said with the ball rolling down the hill, when you put it in motion, you can get it to do some work. And as we see here, these units of charge, these electrons, they move. Now, left to themselves, they're just going to move to the left and to the right and to the left and to the right. And I'm drawing it here. It's depicted left and right. But in the material, there's an up, down, left, right, all over the place, right? Now, they can move in either direction. And what we're calling current is the movement of this charge, these free electrons, as they go from valence from one atom to another and to another. And so current is the movement of charge through a conductor over a period of time. So what do you need? You need a change in charge measured as delta Q for coulombs, and delta T time, that's called an ampere or an amp, right? And ampere, again, is also somebody's last name. And so when you talk about the rate of flow of charge through a conductor, that's called an ampere, and that's called current. Okay, any questions about this? Make sense? No? Okay. And so current is a rate, and current, if someone's electrocuted, is what makes it fatal, right? The voltage doesn't kill people, the current does. All right. And so 1,000 volts seems like a lot, but that's not what's going to kill a person. It's the current. And remember, as in the case with the static electricity, if you don't provide a way for that flow of electrons, that current, to reach the stable ground configuration, it's going to do it through you, right? And we'll talk a little bit more about that. And so in the following slide, talks about some measurements of current and what they do to people. Now, M stands for milli, A is ampere. So milli is 10 to the negative 3. So between 1 and 5 milliamps, you get a little shock. Yeah, no big deal. I still do sometimes, but when I was younger, I'd take a 9-volt battery. You want to test if it's still good, you just put it on your tongue. You go, oh, yep, it's still good, right? You're not going to do that with something in the wall. That'll kill you, right? And so at 60 to 30 milliamps, you start to get loss of muscle control. Why? Because sodium and potassium ions creating a current, voltage, charged particles going through your neurons is how your body triggers your muscles to expand and contract. And so when you get 6 to 30 milliamps, it's painful, quite painful. You can lose muscle control. That's where tasers and stun guns operate. You might read a spec on it and it'll say 10,000 volts. You go, wow, that's a lot. It's the current that's causing that disruption. When you get 50 to 150 milliamps, severe muscle reactions, body really doesn't like that range, possible respiratory arrest. Your lungs might not function. That's where it gets pretty serious. 1,000 milliamps, which is 1 ampere, to 4,300 milliamps, your heart's going to stop. You're going to have irreversible nerve damage and likely pass away. When you get to 10,000 milliamps or 10 amps, that's where you get a lot of severe burns and death, certainly so. And so this is just to say that you don't want to mess with current. Current is drawn, not pushed. And I'll explain what I mean about that subsequently. But when you have a high current line, you want to exercise caution. If you've ever dealt with a car battery, like you're doing, jumping a car, there's a specific order that you attach the leads because you don't want to make yourself the path to ground. You want to make the car the path to ground. Okay? All right. Any questions? No? All right. And so this is a battery from a popular company, and this is a AA battery. And AA batteries are typically, or always, 1.5 volts. And a volt is a unit of storage, so-called electromotive force. And as we said, these free electrons will bounce around left, right, up, down, but you need something to push them in one direction. And that's this voltage. And this voltage is a lot of accumulated charge, more than what transiently happens just through the normal motion in a conductor. In fact, if you had a long enough conductor, and when I played bass guitar in high school, we would take the patch cord 100 feet and we'd stretch it along the highway, the hallway rather, to get all the knots and other tangles out, and you'd hear the radio station on the speaker. And the reason for that is there is electromagnetic energy in the atmosphere, and it was a long enough conductor that EM radiation was moving those electrons in a specific way, and it was coming out as a signal. But that being the case, this voltage is the electromotive force. It's a densely packed amount of accumulated charge that when you give it a place to travel, to move, it will push its way in one direction. And so this is a battery, and this voltage is a form of potential energy. The bigger the voltage, it's like saying the higher the hill that the ball is on. It wants to move and do something, okay? Now you take this battery and you give it now a place for the electrons to move. You lay down a conductor in a path, and this path is called a circuit. an electrical circuit. And because the free electrons can easily flow on this conductor, the electromotive force, this potential energy, is converted into energy of motion, the flow of electrons. And so it pushes the charge, and yes, it does go down through this way, around through the conductor, and back around to the other terminal. Now, when you look at these batteries, you often see something called the plus terminal and the minus terminal. The little button on top, that's the plus terminal, and the flat part, that's the minus terminal. That'll be important in practice over time. So now you have a path for these electrons to flow because you have a conductor and you have this potential energy or electromotive force in the battery. So now you're going to push these things. And when you take a multimeter, and you put one terminal here, one terminal there, it'll actually tell you how much current, how many amperes or milliamperes are flowing. Okay. Any questions about this? Okay. So you can take this battery and you can put together a bunch of batteries. In this case, we said a battery is like potential energy. And if you have a ball and you raise it up 4 feet, if you were to drop it, that energy of motion would perform a certain amount of work. If you added to that 4 feet, another 4 feet, that'd be twice as much energy you're storing. The same thing happens with batteries. If you put 2 batteries in so-called series, that means you have the plus terminal on top, the minus terminal on bottom, then the plus terminal and a minus terminal. The electromotive force stored in these batteries is additive. It adds together. So 2 of these 1.5 volt batteries in series acts like one 3 volt battery because the electromotive force adds. But that's the potential energy. The kinetic energy has not changed. It's the same current, but it's a bigger voltage. There's more pushing force that's available, but the current doesn't change because it's just one pathway. Does that make sense? All right. Any questions? No? All right. So what if you inserted a bulb into this circuit? Well, the bulb has metallic elements. It's a conductor. And so we said these free electrons flow through the conductor. They make their way to one terminal in the battery, inside the battery, into the special metal filament, makes its way through the filament, back to the other terminal, around to the circuit, return back to our battery. Now this bulb has a material in there. It's a conductor, but it's not a very efficient conductor. And what I mean about that is that some of this charge is converted into heat and into photon energy. And so it's because this filament is effectively burning is why you get light. And so energy is conserved, meaning that some of the energy is making its way out here, back. Some of the energy is being converted into heat and into light. Okay? All right, any questions about this? No? All right. And so the bulb is an actuator that tied into last time. It transforms energy from the flow of electrons, electromotive force, into heat and light. And this actuator projects this heat and light into the environment. Okay. And so what if then we arranged 2 batteries in the following fashion? This is a so-called parallel configuration. Parallel, because if you look at the batteries, they're parallel to one another. All right. So what happens? We said the battery has this densely packed set of electrons, charge accumulated, and they want to push their way out. Okay. Well, if this one is pushing down, this one is pushing down, the 2 are joining at the conductor. And so the pushing force is increasing. Whenever you have 2 batteries, so-called in parallel, the currents add. So the pushing force, the flow is going to increase, but the voltage does not change because they're the same height. It's the same potential. Any questions about this? Does that make sense? And so one of the things that you'll see, no, I'm jumping ahead. All right, never mind. Scratch that. All right, so the pushing force is greater. And again, current is not given, it's drawn. And so when I say the pushing force is doubled, If you have a component like a bulb that needs more current in order to light, this parallel connection is more able to deliver that current than this series connection. Current is drawn by something. It's almost like these devices are thirsty. Some will drink more water, want to pull more water through a pipe than others. Current is pulled by the component. It's not pushed by the battery, even though I just called it electromotive force. Okay? But any questions about this? All right. And so in doing work, the unit of measurement for the work that is done is called a watt, and watt is somebody's last name. And power is measured in watts, and power is what is needed to run. Now, a watt is related to a so-called horsepower. And when you see car commercials, you say it's 168 horsepower. And they say so many foot-pounds of torque, right? Now, a horsepower, back in the day, I don't know how long ago, it was the amount of work that can be done by a single horse. Go figure, it's persistent. Now, horsepower is the amount of power, and it's work applied over time. It's the amount of power needed to lift 550 pounds 1 foot in 1 second's time. Now, of course, when you're lifting something, yeah, you might be able to lift it, but can you lift it in 1 second? That's the difference about power. It's the applied energy in a specific unit of time. Now, power is equal in electronics to voltage times the current. And 1 watt of power is 1/746th horsepower. That might not seem like a lot, but when you take a bulb, 60-watt bulb, 120-watt bulb, that's kind of a bit of work, right? It's electrical work, but we're relating it to mechanical horsepower. Now, 1 kilowatt, which is typically what they measure household current as, so many kilowatt hours of electricity, is 1.340 and change mechanical horsepower. Can you perform mechanical work with electricity? Absolutely, but you're going to lose some of that due to friction. Okay? All right. Any questions about this? Does that make sense? Yes. I is current in amperes. I forgot to mention that. Thank you. So LED bulbs are more efficient, and we contrast what happens in this regular bulb, so-called incandescent bulb. We said that the filament heats up. And because it heats up, not only are you generating light, but some of that energy is being dissipated in heat. If you go to a bulb and you put your hand on it after it's been on, you can feel some warmth coming from it, right? And so an LED converts more of its power, electrical power going through it, to light, and relatively much less than the incandescent bulb as heat, which is why LED bulbs use less power. And if you go to like Home Depot or Lowe's or what have you, a hardware store, and you see these bulbs and it says a 60-watt equivalent, but if you look at the actual bulb spec, it only eats 8 watts of power, right? They're more efficient for the amount of light generated, okay? Because less is being dissipated as heat and more of it is light. Okay, any questions about this? No? Makes sense? No? All right, so this is a Tesla Model S battery, and it goes underneath the chassis. It's pretty weighty, about 600 to 800 pounds, because batteries have mass. All this stuff weighs a bunch because there are metals and chemicals and other compounds in them. If you take one of these modules and you take it out, this is what it looks like. And this is the battery module. And there are lots of people who take them apart, take out the battery cells, and these look like AA's, but they're not AA's. They're much larger than AA's. Why do people do this? Well, because for the price, that's a pretty good deal for all those batteries. And people harvest them and use the rechargeable batteries for other purposes. Okay, don't try this yourself because there are many opportunities to electrocute yourself, right? It's not that deep of a concept. You just have to understand about the dangers of current and voltage. And if you watch videos where people do this, you notice they're very careful in wearing rubber gloves. Rubber is an insulator, and making sure that they're unplugging stuff and not shorting things. Okay? All right. So if we look at this battery module has, and we'll call a row going left to right, 6 battery cells per row, and there are a total of 74 rows. That's like 400 some odd batteries. That's not bad for just $1,500 and change, right? You have 440 something batteries. That's pretty good for battery, for rechargeables. Going to like Best Buy, you buy 4 rechargeable AA's, it'll cost you like $9 or $12, right? So that being the case, inside this module, each of these rows is connected in, see, 20.8. Yeah, each one of these is connected in series, right? And so the voltage for one battery is added to the other. And so that's 3.8 times 6 is 22.8 volts, right? So each row is connected in series, and then each one of these rows is in parallel. So it's adding the voltage for all the batteries in a row, and across the rows, it's adding the current. And if we look at the type of current that this thing can provide or can deliver, the max discharge current for 10 seconds, if you tried to pull out of this the maximum flow of electrons that it could give you 750 amperes for 10 seconds. That's an astonishingly large amount of current. So that's just to say what you can do by putting together these series and parallel connections among batteries. You can effectively create the battery that you need in order to drive your circuit. And typically, when you deploy a circuit or you enterprise to design something, there's this thing called your power budget. You take all the components you need, how much voltage and current do they require, and you add it all up, and you need a battery that's at least that big. Okay? All right. Any questions about it? No? All right. So let's take a look at some electronic so-called components. We talked about bulbs. That's an electronic component. It projects energy into the environment. It's an actuator. And when we have charge going across a component, each component to a degree, or device to a degree, resists the flow of electrons or inhibits the flow of electrons to a degree. Now, resistance is the measurement of how much a particular component inhibits electrons. Now, the generalization of resistance is called impedance, and that's beyond the scope of what we're going to do in this semester. But that being the case, you measure resistance in a unit called ohms. OHM is someone's last name, and it's what you use to measure this pushing back against the electromotive force that wants electrons to flow through the circuit and also through the component. The result of this is a so-called voltage drop, a reduction in the amount of electromotive force on account of that component, our bulb. Any questions about this? No? Now, something called Kirchhoff's law, or Kirchhoff's law, Kirchhoff is somebody's last name, it says that the amount of electromotive force going around a circuit sums to 0. If you have a ball rolling down a hill and that ball has a certain force behind it, and you have some barriers that the ball hits, if the ball eventually comes to 0, then each barrier that ball hits subtracts some of that force, including friction with the ground. In similar fashion, this electromotive force, as you go around the circuit and encounter a number of components, each one, to some degree, drops that electromotive force. Does that make sense? Any questions? No? All right. And so this is a component called a resistor. And a resistor is governed by Ohm's law. And when I was a EE student, we called it Irv's rule because if you rearrange it, it's IR equals V. That's how we remembered it. And what it says is there's a linear relationship between the voltage across the resistor, voltage drop, reduction in electromotive force, and the current going through it. So if you have a bigger resistor, R, and the same voltage, which you do because you have a battery, that means the current is going to be less. If you have a smaller resistor, R, and it's the same battery, voltage V, that means the current is going to be more. So effectively, what you can do with this resistor is reduce the current that is perceived by all of the components that follow the resistor. And in the circuit we're going to build on Friday, we do exactly that with a 220 ohm resistor, because that's how you protect an LED from burning out and also protect the digital I/O pin on the Arduino from being burned out. Okay? All right. Any questions about this? No questions? Make sense? Yeah? All right. And so how do you determine what the value of electromotive force blocking that a resistor has? Well, it's coded using color bands. Now, when you have a color band, one side of the color band will be one of these colors like white, gold, or silver. You want to make sure that color band is on the right-hand side, because that's what's called your tolerance. That's how much wiggle fudge factor the blocking force of this resistor has. The other bands are used to encode the resistance in ohms. Now, there are so-called four-band resistors. With a four-band resistor, of course, that last band here is gold. It's a tolerance of 5%, but the first three bands encode the resistance. The first band and the second band are numbers coded by this chart, but the third band in the four-band resistor, that's called the multiplier. And so here is an example. We have a 270 ohm resistor with a 5% tolerance. And when you buy a component, if you have a tighter tolerance, a smaller percentage, that's going to cost you more. That means it's going to give you this type of blocking power, but it's only going to vary a slight amount. Now, why do you need that? Because sometimes when you design a circuit, things have to be very precise. You have to pay for the extra engineering that makes things more precise. And so here, 270 ohm resistor, we have red, which is 2. We have violet, my colors are bad, which is 7. And then we have, looks like brown, which is 10 to the 1. So that's 27 times 10 to the 1, which is 270. Likewise, and I won't do that example, for the 5-band resistor, that last band is a tolerance, and the tolerance is really tight. It's a 1% tolerance. We usually don't talk about that because they're very expensive. But the first 3 bands, those are the numbers by the chart, and that last band, so that's 100. That last band is orange, which is 3 times 10 to the 3. Okay, I just did it. Any questions about that? So when you search for a 220 ohm resistor, it'll be labeled, but you should get comfortable reading the bands and knowing how to calculate that yourself. Any questions? No? All right. So in electrical engineering, they often give additional or different names to various denominations of things like current, voltage, capacitance. And it's usually based on 10 to the 3, multiples of 10 to the 3, right? And so here, 10 to the 0 is just the unit. So 10 to the 0 is just 1, you'd say 1 amp. But if you had 10 to the negative 3 amps, that's called a milliamp. If you go up with these fractional components, it goes milli, micro, that's 10 to the 6, nano, 10 to the minus 9, pico, 10 to the minus 12. So if you had something that was 10 or 5 microamps, it would be 5 times 10 to the minus 6 amperes, right? And so oftentimes when you look up specifications, they're going to use these names. Why? Because it's easy to get it wrong if it's a number. It's harder to get it wrong if you're actually writing out a name for things. Okay? Right. Any questions? No? All right. And so these are various components. And one of the things you'll see is these symbols for the components, because when you see a circuit diagram, they don't have a picture of a resistor. They have the diagram, and they have the conductor is just a line in some color that connects together these various components. And so here, we'll start out with something called a potentiometer. A potentiometer looks like a resistor. It has this jagged pattern here, that's a resistor, but a potentiometer has this little dial. And when you turn the dial, you're changing the resistance within some range, right? And so here for a potentiometer, you connect your voltage on one side, ground to another side, and as you turn the dial, it's effectively changing the resistance. You can imagine that line changing. So if you have a potentiometer in a circuit, you have your battery somewhere, you'd have your conductor connect here, ground or minus, connect here. Okay. All right. Any questions about this? No? All right. This other one is called a diode. A diode is a semiconductor, and a diode has two parts, one called the anode, which is the positive terminal of the diode, and one called the cathode, which is the negative terminal of the diode. Now, the anode is the part of the diode, I hope I get this right. Yeah, part of the diode that has this stripe on it, right? And so you have the symbol and you have the actual component. So this is the positive side, this is the negative side. Now, what does a diode do? A diode allows the free flow of electrons, but only in one direction. It allows the free flow of electrons if you have the positive side connected to the positive terminal of the battery, negative side to the negative terminal of the battery or to ground, electrons will only flow in one direction, but not the other. Why is that useful? Because when you're trying to shape the value of current, some types of current will go negative, and you don't want, for some components, your current to go negative. Current that comes out of the wall, it acts as a sinusoid, and it goes positive and goes negative. The reason for that is that varying current transfers easily over conductors over long distances. That's how they transmit power to houses. But many devices have current that's just a single value, so-called direct current. And a diode is a one-way switch, so to speak. It passes current in only one direction, from anode to cathode. Or if you're talking about the free flow from the bottom of the battery up in this direction. But if you were to reverse the battery, it wouldn't work. Okay? All right. Any questions about this? The other one is called the light emitting diode, or LED. It's just like a diode. It has an anode, a plus side, and a cathode, a minus side. But this one also has a little filament in there that'll produce light. Now, when you have the actual component, the leg or conductor of the diode that is longer, that's the anode, that's the plus part or the plus side of the diode. Any questions about this? So it's a one-way switch that also lights. So think of it as a one-way light bulb, so to speak, okay? If you reverse the current or switch the battery, this thing won't light. If you have the battery in the quote unquote right direction, it will light, okay? All right, any questions? No? All right. This is a switch, and a switch breaks the circuit. Well, this is the diagram for a switch, and there are all sorts of switches. And these are two examples of a switch. This is called a knife switch, kind of like in the movies, Frankenstein and the, things. And this is called a single pole, single throw switch. With this switch, you hold it, and as long as you're holding it, it's switched on. And if you release it, it pops back. There's something called a single pole double throw switch, which says if you pull it this way, it'll stay off. If you push it that way, it'll stay on. And there's all sorts of variations that we can talk about when the time is appropriate. Any questions about this? No? All right. And so this is called ground, and ground is a symbol that represents this stable state, this reference point, and current wants to go to ground, right? And so in every circuit, and I'll show you an example, you'll see where the ground plane is, and the negative terminal of the battery is often drawn as being connected to ground because that's the reference point for your voltages. All right. So ground is called ground historically because of power distribution. And most modern construction, not even modern construction from the 80s, and they've been doing this, if you go near the electrical panel for a house, you'll see a metal rod that has been driven about 8 feet into the ground. And there's a thick wire or cable that goes from that metal rod. This is what it looks like. And it attaches to your electrical panel. That's called the ground rod. And the reason for that has to do with lightning and power distribution. Now, of course, if lightning strikes, it's trying to find a path to ground. If you're not at ground, it'll treat you as ground. And so you have all these metal pipes and things coming into houses. And if there's a lightning strike nearby, you don't want electricity to find your pipes just as you're turning on the shower, right? You can be electrocuted. And that actually used to happen. And so with this ground rod, it provides that same reference to ground, that stable state that's associated with the power utility, the electrical panel. so that when you plug in your appliances, that appliance has electricity going into it, but it's also connected to ground through your electrical panel, which has that grounding rod. Now, what that means is that should something happen, you touch your metal fridge, you're not going to get electrocuted because of this ground rod. And it was originally called ground because of driving rods into the earth, into ground. Any questions about this? No? All right. So this is a capacitor, and a capacitor has two conductors, and sandwiched between those conductors is an insulator. It's called a dielectric. And what happens is if you build up enough charge on one of the conductors, one of these plates in the capacitor, it's like lightning. It'll build up so much that it will overwhelm, it's wanting to go to ground will overwhelm the insulating properties of the dielectric sandwiched between these two plates. And so essentially what a capacitor is, it's kind of like a little mini battery, right? It stores charge, and then if enough charge accumulates, it'll discharge it. It'll send it across this dielectric to the other side. Now, a capacitor is used when you're trying to smooth out a signal. Suppose you have current, and that current looks like a sinusoid. What'll happen, the capacitor will charge when the voltage is increasing, and then when the voltage starts to drop, the capacitor will start to discharge, and then it'll start to charge, and it'll start to discharge. And so what'll happen is what used to be swinging very high and low in oscillating or changing voltage effectively will look like this. It won't oscillate as much because of the capacitor. Now, some devices have really big capacitors as a way to protect against power flickers, right? Because if you have the power shuts off, especially for things like power supplies for computers, you don't want your computer to get 0 volts because it'll shut off, right? And so they use the so-called smooth, unstable current, okay? Are there any questions about this? Yes. Mm-hmm. Yes. Mm-hmm. Yes. The black box has capacitors, but it also has something called an inductor. And I can talk, and a Wheatstone bridge, a rectifier. And so you have this oscillating current that looks like a sinusoid, and you need to do a couple things. You need to make the negative part of the current positive, right? Because you can't have positive voltage in DC. You also need to take the 120 volts that's in the wall and shape it down to 24 volts. So it does what's called a step down, and that's using 2 electromagnets. And the more coils your electromagnet has, put one close to the other, the amount of reduction in current in the other is proportional to the difference in the number of coils between the two. So you have a step down on voltage, you have the capacitor to smooth the signal so it doesn't go negative, and then you have a bunch of diodes in a rectangular pattern called the Wheatstone bridge to make sure it never drops negative. So to answer your question, yes, but there's a bunch of other stuff in there that's beyond the scope of this course. And in electrical engineering, they have a whole course that deals with what happens when you have sinusoidal current, and that's analog system design. But we're going to kind of cover a little bit in terms of resistors, but we're going to keep our focus on the digital and DC current, direct current that doesn't change in time. Okay, but yes, a long story to it. Yes, it does, but it has other stuff as well. Okay, any other questions? No? All right. So that's a capacitor, and charge accumulates, and the charge on this device, the capacitor, is equal to the voltage times what's called the capacitance. And when you see capacitance, the unit is called a farad, F-A-R-A-D, which is also somebody's last name. And so you'll see microfarad, millifarad, picofarad, nanofarad. But if you go to some devices, you'll see a 1 farad capacitor. Those things are huge. They're like small garbage cans. You don't want to mess with capacitors. And in fact, if you're doing electrical work, things like your washing machine that has a huge motor that can store charge, you want to make sure that your appliances have discharge, because even if you switch off your electrical panel, you can still get a pretty nasty shock because you have all of these appliances storing charge that need to discharge before you can do your electrical work. Any questions about that? No? All right. So some components, they do things, but you study what they do and what they bring to bear and how they change the appearance of your electrical signal so you can get it to do things for you in various ways. Okay, so we only have 2 minutes. In electronics, it's about forming, changing, and shaping your electrical current. This circuit is called the voltage divider. So let's say if you have a battery that's 24 volts and you only need 16 volts or 6 volts. How do you take a 24-volt battery and turn it into a 12-volt battery? Well, you use resistors to do that. And this particular circuit is called the voltage divider. And so using Kirchhoff's law, the voltage drop, it sums to 0. So if you have some voltage, 24 volts here, it's connected to ground. This is the symbol for a battery. The longer line is the positive terminal of the battery. The shorter line is the negative terminal for the battery. And so current will flow. It flows across the resistor 1, and it flows across resistor 2. Here, VR1 is the voltage drop across resistor 1. VR2 is the voltage drop across resistor 2. Now, V0, that's going to be the output voltage that you want. And so you select your resistors such that R2, the bottom resistor, divided by the sum of those two resistances, that's going to be the proportion that you see at V out. So if you had a 24-volt battery and you wanted 12 volts at V out, R1 and R2 would be the same resistance. If you wanted something that was 3/4, the proportion R2 over R1 plus R2 would be 3/4. And so this is an example of shaping the electrical signal. And that's what these components are intended to do. This, and I'll end here, we only have 10 seconds, is the so-called brain fart, chaser circuit. And here you'll notice, and this is the point I want to make, you have some LEDs connected to ground, driven by the digital I/O lines, but you have some resistors that are 220 ohms. And the purpose of that is to drop the voltage such that you're not going to pull more current than the digital I/O lines can deliver. So we'll end there, and we'll meet back up on Friday. Question? Okay, this one? Yes. And all of this is on the Blackboard. I'll see what happened to the recording. Let me return your thing. Let me stop the share. Stop the recording.